Okay, so this video is going to look at the follow-on from sort of a basic introduction to equilibrium. So it's very, very important at this point that you are happy with what an equilibrium is, the idea of reversible reactions occurring in a closed system, and the key characteristics of that, particularly that there's a forward and a backward reaction that are occurring. So let's assume that we're happy with all that, and we've got a system that is at equilibrium. Now, that system behaves in a very, very strange way, and there was a French scientist, a guy called Henri Louis Le Chatelier, who came up with a principle to define how that equilibrium would react, particularly when we try and make changes. So Le Chatelier said that a system at equilibrium, these weren't his exact words, and they were probably in French, a system at equilibrium will act to undo changes made to it. So what that essentially is saying is if we act to change the conditions of a system at equilibrium, the equilibrium will actually act to undo those changes. It will try and reverse what we've done. Now the changes I'm referring to here they fall into three categories. So the changes are to the temperature, the changes are, and this is of the system at equilibrium, so we can change the temperature, we can change the pressure, or we can change the concentration of reactants or products, and that will become hopefully more clear later on. So, Le Chatelier, system equilibrium will act to undo changes made to it. The changes I'm talking about are temperature, pressure, and concentration of reactants or product. That equilibrium can only undo these changes in one of two ways. It can either increase the forward reaction or it can increase the backward reaction. And it will do that until it has partially undone the change and equilibrium has been re-established essentially. So I'm going to go through these changes. So first of all, temperature. So what's going on here? So we've got a system at equilibrium. Let's imagine that we've increased the temperature. Now, according to Le Chatelier, the equilibrium will now act to try and decrease the temperature. So we increase the temperature, the equilibrium wants to decrease the temperature. And as I said, the only way it can do that is by increasing either the forward reaction and therefore breaking equilibrium, or it can increase the backward reaction until it's happy with basically the change it's made, and then it will re-establish equilibrium. The key thing about this is really to understand that this idea of increasing temperature, well, what does that actually mean? So if I have a system, and I'm talking, when I say system, a container of some sort, something where the equilibrium is taking place. That could be a beaker, it could be a box, a gas canister, whatever. If I increase the temperature, all I'm doing is I'm adding thermal heat energy to the system. So I'm adding energy, particularly in the case of thermal heat energy, to the system. And I think it helps to almost think of that energy as just sort of floating about. It's what's allowing the temperature almost to be increasing. So it's energy that's just free floating there around. It's not energy stored within the reactants or the products. So if I now apply this and I say, right, let's imagine an equilibrium, and that equilibrium just really, let's actually imagine an equilibrium now, a really simple one that doesn't exist because A, B, C and D aren't real things, but we'll say that we've got a system, and within that system we have A, B, C and D present, and they're reacting, and they have reached equilibrium. Now I increase the temperature, I add some thermal energy to this container that contains these reactants and products. I add the energy. The equilibrium is going to try and reduce that energy because that will allow it to reduce the temperature. But how can it do that? It needs to somehow take energy in. It needs to take in the heat energy. Well, that's this idea of exothermic and endothermic reactions. Exothermic reactions release heat energy, endothermic reactions take in heat energy. So when we look at this equilibrium that is established within this closed system. One direction, and you need to be told this, one direction will be endothermic and one direction, the opposite, will be exothermic. Now for the sake of this particular example, I'm going to say that the forward reaction is exothermic. So I increase the temperature. The equilibrium, the system, wants to decrease the temperature. So I've added extra energy into this system, more energy floating about. What the equilibrium is going to do is it is going to favour the backward endothermic reaction. Now that's only true for this particular example because I've said the forward reaction is exothermic. The opposite would be true if the forward reaction was endothermic. So it favours the backward endothermic reaction because what that's going to do is it is going to take in energy. Energy is going to get taken in, and that energy is going to move from being free floating heat energy, it's going to move to being stored as chemical energy within the substances in this reaction, this equilibrium. So I increase the temperature, I'm adding thermal or heat energy. The reaction, the equilibrium, is going to adjust by favouring, increasing the endothermic reaction. At that point, there still will be a bit of the exothermic forward reaction, but not as much, and the equilibrium will be broken. It will no longer be occurring, the forward and backward, at the same rate. The backward reaction in this case now is occurring at a much greater rate. The endothermic reaction is dominating out of the two. It's taking in the energy, until eventually it's taken in quite a lot of the energy. It won't get back to where it was. It takes in quite a lot of energy, and now we're in a situation where equilibrium will be re-established and the forward and backward reaction rates will ultimately end up being equal again. So, if I increase temperature, the endothermic reaction is favoured, or increased if you prefer that as a term. This means, in terms of position of equilibrium, the position of equilibrium shifts in that direction, the direction that is the endothermic reaction. So in my terrible example above, in this particular instance, increased temperature, because the forward reaction is exothermic in my example, the backward endothermic reaction is the one that's going to be favoured, it's going to be increased, and therefore the position of equilibrium shifts to the left. It shifts in the backward direction. Opposite is of course true. If I were to decrease the temperature, the exothermic reaction would be favoured or increased, the exact opposite here. And the position of equilibrium shifts in that particular direction. So for my example above, if I in this one were to decrease the temperature, I'm taking away some of that heat energy, that thermal energy that's present in the system. It wants to replace that, so the exothermic reaction, if I decrease temperature, the exothermic reaction would be favoured, would be increased. The position of equilibrium would shift to the right. More heat energy would be released into the system, and ultimately then we would re-establish equilibrium after a while. So that's how temperature, that's how an equilibrium changes, adjusts itself to undo temperature increases or decreases. So there's also pressure though. You think, well, what happens when we increase or decrease pressure? So same thing's true of the last one, in that if I increase the pressure, the equilibrium wants to decrease the pressure. This Le Chatelier's principle. Whatever we do, it tries to undo it. Now this one is slightly odd. It depends on the stuff that's on the sides of the equilibrium. So if I again use the exact same one as I used before, my A plus B, in reality obviously these would be real substances, but I'm just using made up ones. I think it just makes it a bit more simple. So here's my system at equilibrium once more. A plus B is in equilibrium with C and D, all within this closed system. If I increase the pressure, The system wants to decrease the pressure, so it favours either the forward or the backward reaction. Fine. But how can it do that? How does that affect the pressure? Now, an analogy for this would be the idea of a crowded room. If you imagine you've got, I don't know, a classroom where you've got 20, 30 people in that classroom. If you increase the pressure, that's essentially like making the classroom smaller. So this big classroom with 20, 30 people in it, we now make that classroom a lot smaller. We increase the pressure and it becomes a lot more crowded. This idea of increasing the pressure now, the room is a lot more crowded. Those same 20 or 30 people are within a smaller space. So it's a lot more crowded, it's a lot more uncomfortable. Now, in that room situation, the way you can fix that is by getting rid of some of the people from the room. Send some people out so it now becomes less crowded, less cramped. And it's the exact same principle with this as a reaction. When we increase the pressure, the reaction tries to react to get rid of stuff so there is less stuff in the system. So here's my system there. A, B, C and D are present. Now in this situation what we've got is we have to look at how much stuff there is. I'm using this term stuff because I just think it's much easier. The reactants, products, molecules, moles, whatever, stuff on each side. So on this side I've got one A and one B, 1 mole of A, 1 mole of B, 1 molecule of A, 1 molecule of B, however you want to see it. So I've got 1 plus 1, I've got 2 stuffs on the left hand side. On the right hand side I've got 2 moles or molecules of C and 1 mole or molecule of D. So therefore I've got 3 stuffs. So I have got more stuff on the right hand side than I have on the left hand side. Therefore if I increase the pressure, what this reaction can do is it can say, right, it's getting cramped in here, it's getting crowded, the pressure has been increased. What I can do is I can favour the backward reaction because that turns 3 things into 2. So if I keep doing that, I'm turning 3 things into 2. I'm going to end up with less stuff in the container. So it ends up becoming less crowded. So 3 things becomes 2. And then the opposite, if I were to decrease the pressure, the reaction would adjust, the equilibrium would adjust itself, and it would favour the forward reaction in this instance because the forward reaction produces more stuff. So it's like having that classroom and making it bigger. There's too much space. We now add more people. It would favour the forward reaction, and 2 stuffs, 2 things, moles, molecules, would become 3, therefore adding to the situation. So in terms of how to word this, if I increase the pressure, it shifts, it favours or it increases, increases reaction that produces less stuff. And by stuff I'm talking moles, molecules. And again, that means therefore that the position of equilibrium shifts in that particular direction. So from my example above, if I stick with this idea of increasing pressure, I increase pressure of this system, the reaction, the equilibrium adjusts itself, it shifts in the direction that has less stuff to, this case, the backward reaction, and therefore the position of equilibrium shifts in that backward direction. If I were to decrease the pressure, it would favour increase the reaction that produces more stuff. And as per the other one, the position of equilibrium would shift in that direction. So if I were to decrease the pressure, this case the forward reaction, because it produces more stuff, would be favoured, therefore the position of equilibrium would shift in to the right in this particular instance. Okay, final one. I'm going to look at concentration, then look at just a little bit about yield at the very end. Okay, concentration is actually, out of the 3 of the changes, is perhaps the more simple one because it's less sort of weird theory behind it. Same principle is true though, that if, according to Le Chatelier, if we increase the concentration of something within the equilibrium system, then the reaction will try to reduce it. So if I again just go back to my A, B, C and D, if I increase A, the reaction, the equilibrium, the system wants to reduce how much A there is. If I increase C, it wants to reduce how much C there is. If I decrease D, it wants to increase D. Whatever it is you do, it tries to do the opposite. And it does this again by favouring a forward or the backward reaction, and therefore the position of equilibrium shifts in that direction. So If I were to decrease A, for example, the reaction would favour the direction that produces A because it wants to make more of it. If I were to, let's say, increase A, it wants to decrease that, so it would favour the reaction which uses up A, in this case the forward one. So however this works, and this is a difficult one in some ways, so I have to increase X, and I'm just going to say whatever X is. X in this case could be A, B, C or D. So if I increase X, the reaction that uses X will increase. So to put that in context, if I increase A, the reaction that uses A, in this case the A and B, the forward reaction, that will increase. So of course position shifts in that direction. And then if I were to decrease X, the reaction that produces or makes X will increase. And again, position of equilibrium shifts in that direction. So using my example above, again sticking with A, if I were to decrease A, I would find the reaction that produces A, which in this case is the C plus D, the backward reaction, that would increase. The position of equilibrium would shift to the left. If I were to increase C, this reaction here, which uses C, would increase, so it would increase the backward reaction. The position of equilibrium would shift to the left. So it's all about realising, basically, again, this idea of Le Chatelier's principle. You're undoing the changes that are being made. You have to spot, though, where the thing that's being stated in the question, where it actually sits in the equilibrium, on which side it is, as to how to adjust that. The very final bit, just to talk about, really, is something called yield. Now, yield is something that you hear in sort of farming terms, the yield of a crop. High yield, we assume is good. High yield is good. It means you have more of the thing. Now, in terms of industry, let's think of a reaction. Again, a slightly just different one that I've used previously, but it's the same idea. Now let's assume this is an industrial process and I really want to produce C. C is a substance which I absolutely want because I can sell it and make billions and billions of pounds. And this is the reaction that is used to produce C on an industrial scale. Well, I can utilise as a scientist, as an industrial person, I can utilise this idea of changing conditions to make more of C. So I want to look for conditions that are going to favour the forward reaction and essentially going to shift the position of equilibrium to this direction because that's going to make me more C. So in this particular instance, I can use this concept of changing temperature, pressure and concentration. I could say, right, let's assume for this argument, for this question, the forward reaction is endothermic. Again, in an exam, you would be told this. But let's assume the forward reaction is endothermic. I want to make more C, so I want to shift the position of equilibrium to the right. I want to favour the forward reaction. So if the forward reaction is endothermic, and endothermic takes in energy, well, if I increase the temperature, this is just using the concepts from above. If I increase temperature, that means I add energy. The equilibrium wants to undo that energy, so it would increase the endothermic reaction. Well, in this case, that would be in my right hand, the forward reaction. So the position of equilibrium would shift to the right, and therefore it would get C, more C. So the key thing here is that to increase yield, you want the position of equilibrium shifts towards it. So I'm trying to factor everything. I've already said this, but I just thought I'd write it down. I'm trying to get my position of equilibrium, my reactions to favour, to shift in the direction of C. So I can increase the temperature. Now in terms of pressure, well, what have I got? Let's count my stuff. I've got 2 things, 3 things. So I've got 5 stuffs on this side. On this side I've got 1C, 3D, so I've got 4 stuffs there. So I've got less stuff, less moles, molecules on my right hand side than I have on the left. So in this case, if I were to increase pressure, I've made it more crowded. It wants to undo some of that crowded, so it turns 5 into 4. It reduces some of the stuff present in this closed system, and it would favour the forward reaction. It would shift the position of equilibrium in the right-hand direction, therefore giving me more C. Now you could also, in theory here, maybe not as easy, if you increase the concentrations, increased A or B, that would also favour the forward reaction. If you added more A and more B, it would force it forward because it wants to undo that change. Go, 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 go. Other thing you could do is if you reduced C, if you took C out as the reaction was occurring, provided it was in a situation where you could do that, maybe it's produced as a gas and everything else is a liquid, I don't know. If you can somehow get rid of C, then the reaction would shift to the right again, forward reaction, in order to replace C. The idea here is just applying this concept of changing conditions and how that would affect yield on an industrial scale. Weird topic, I appreciate. Go back, pause, re-watch. Hopefully that's been of some help, but that is how Le Chatelier's principle can be used to change conditions within equilibria.